Hello everyone. Today I'm going to be talking about rings. If you've been keeping up with the series, sorry for the long delay. My microphone kind of stopped working. If you've been keeping up with my sort of community posts on my page, I've been kind of posting about it. My microphone died, and then I just moved back on campus for the school year. So I ordered a new microphone, and it like didn't get processed in our college's like UPS place for like almost 2 weeks. So yeah, I just got it a few days ago. Um, so now I'm back recording this series. So anyway, we've departed the land of group theory, although we will see just in a second. In defining a ring, we're going to use the definition of a group. Um, so that's what we're going to start off with. What is the definition of a ring? Well, a ring is a set R with two associative uh, shoot, what's the word I'm looking for? Associative binary operations. And typically we just denote these as plus and times. So addition and multiplication, sort of colloquially. So just to recap sort of what these words mean. Associative means if you have three elements in your set, then it doesn't matter, if you do y times z first, and then do x times that. This is the same thing as if you were to do x times y, and then times that with z. So that's associativity. And then the same thing with plus. Binary operation means it's a function from basically going from pairs of elements in R. You take a pair of elements in R and you assign a new value in R. Okay, and so we've seen a group. The group operation is associative binary operation, but rings have two operations. Now, furthermore, of course, this isn't all. So the first thing is that if you just look at the set R with the addition, this is an abelian group or a commutative group. And the additive identity is denoted just by 0, as usual. Okay, and that's still not all. We also have distributive laws, which say that if I multiply an element with a sum, then this is a sum of multiplications, right? So this is just standard distributive law that we're used to. And then, so this is distribution from the left, and then we also have distribution from the right. Now notice here that our multiplication, so our addition is given to be abelian, right? So it doesn't matter which way we add. However, typically it does matter which way we multiply. This is an x, not a y. So this is sort of the general, commonly accepted definition of a ring. Or I say commonly, but this is like the bare structure. Now, most people, most times you have an identity for the multiplication, which we denote by 1, right? So some people call this a ring with a unit, or a unitary ring, maybe. I'm trying to think of a good... Well, units have another meaning in ring theory. But for what I'm going to do, I'm going to assume that every ring that we talk about has a multiplicative identity, right? And remember, this is just something such that if I multiply, 1 times x, this is the same thing also as x times 1, and this is equal to x. And this is for all x and r. Okay. So in general, you have x times y not equal to y times x. However, commutative rings are studied heavily. So if you've ever seen like a college class called commutative algebra, commutative algebra is literally just the study of commutative rings. So you have commutative algebra, and commutative algebra also sort of branches off. It is very useful in algebraic geometry and also algebraic number theory. Okay. And so for a lot of things, it's kind of more convenient to talk about commutative rings, just because you don't have to deal with a lot of casework. Like there are some definitions we'll see, like for ideals, which I'll talk about in the next video. You have to be careful. You have to define a left ideal and a right ideal, but when the ring is commutative, they're the same thing. Another point is that, in general, x in R has no multiplicative inverse. So obviously for any x, there's a negative x, such that x plus negative x, or we can just write this as x minus x, is equal to 0, right? Because we know that under addition, this is a group, so there's inverses for addition. However, in general, you don't have multiplicative inverses. When you do, you get fields. And I'll actually define a field later, but fields on their own are a very rich subject, and that's sort of going to be the third part of the algebra series, is field theory. And that's where Galois theory comes in, if you've ever heard of that. So here are some examples that you are bound to have seen, and these are the typical numbers. You have the integers, the rational numbers, the real numbers, and the complex numbers. So these are some examples that you probably have seen. For a less trivial example, you can consider the set of functions S to R, where S is any set, and R is a ring. Okay, and the ring structure here is built by sort of adding and multiplying functions pointwise. In other words, for any point in S, f of x is in R, and so you can multiply the f of x's, you can add the f of x's, and so you define functions that way. Okay, now let's get into some sort of basic properties that we can prove just from the axioms that we've stated. So the first one is that 0 times x equals 0. Okay, so let's look at 0x plus x. This is the same thing as 0x plus 1x. Okay, and then we can factor out the x, right, using the right distributive law. Now 0 plus 1, 0 is an additive identity, so this is just 1x, and 1x is equal to x. So therefore, we can subtract x on both sides, right, or take the additive inverse on both sides, and that gives us 0x equals 0 as desired. A very similar proof using the left distributive law will also give like x times 0 is 0. Next thing would be that if we look at the additive inverse of the multiplicative identity, or in other words, -1, and we multiply it by x, this is going to give us the additive inverse of x. Okay, so let's look at why that is. So if we take x plus -1 times x, we want to show that this is 0, right? Because we know negative x is the unique element such that x plus -x is 0. So if this is equal to 0, then -1 times x is -0. And in fact, we can, of course, this is 1 times x, so we can, again, distribute, and we get 1 plus -1, or I'll just write as 1 minus 1 times x. 1 minus 1 is 0, so we have 0 times x, which is 0. So therefore, we get that this must be minus x. Okay. Next, we have that -1 squared is equal to 1. Okay, so why is that? Well, 1 minus 1 is equal to 0. Okay. So let's look at -1 times -1 minus 1. Okay. This is sort of minus, we can look at this instead as sort of plus -1 times 1, okay? And then we can distribute a -1, and then we get -1 plus 1, and then that's -1 times 0, which is 0, okay? And so that shows that whatever this is, it's the additive inverse to this, but this is -1. The additive inverse of -1 is 1, so this must be 1. In a similar vein, you can prove that -x times y is equal to -xy. And the proof is, again, just by looking at sort of xy plus -x times y, factoring out a y, and then you get 0y, which is equal to 0. You can also show that -x times -y is equal to xy. And again, you show this in a very similar fashion. Take -x minus y, -xy, and we can factor a -x, and we get -y plus y, and that's -x 0, which is 0. Okay. So these are sort of basic rules of arithmetic. There's also something a little more complicated, so let's look at the distributive law again, right? So x times y plus z is xy plus xz. Then you can prove by induction that if we keep x fixed, but we keep adding elements in here, then essentially the idea is that this is going to be x times y1 plus all the way to y sub n minus 1 plus x y sub n, right? By using the distributive law, where one of our terms is, this sum here, and then the other one is just y sub n. And so by induction, this is going to give you the sum as I goes from 1 to m of x, of x y sub I. And you can also further generalize this to show that if you have a sum of x terms multiplied by a sum, these are going to be indexed differently, by a sum of y terms, then you can distribute sort of on both sides, and you get a double sum over I and j. So I goes to m, j goes to n, and you look at the products x sub I times y sub j. So for example, if you have x1 plus x2 times y1 plus y2, the result is going to be the sum of all the products xi yj. So you have x1 times y1 plus x1 times y2 plus x2 times y1 plus x2 times y2, which is sort of the typical, you might learn this as FOIL, which stands for first. So you take the first terms and then outer, inner, last. Anyway, so those are some basic properties that we can derive from the axioms. Now we're going to look at some more sort of definitions about rings, right? So the first thing of interest is what a subring is. And again, I'm going to use this notation. If you're watching this without having watched the group theory videos, in the group theory videos, I use sort of the subset notation with a little g to denote subgroup. So here I'm going to use a similar thing, but with a little r to denote subring. So a subring is a subset of R with 1 is in R prime, and if x and y are in R prime, then minus x, x plus y, and x times y all have to be in R prime as well. So in other words, R prime is closed under additive inverses, addition, and multiplication. And we know it's non-empty because it has to contain 1. Okay. So, and so you can check that this actually does define a ring. The operations are, of course, just addition and multiplication for R. Since R prime is by definition closed under these operations, there are going to be binary operations on the set, and then that they satisfy all the other properties essentially just follows from the fact that they satisfy those properties in R. Okay. Notice indeed that 0 is in a subring because 1 being in R prime implies that minus 1 is in R prime, and so therefore 1 plus minus 1 is in R prime, but this is just equal to 0. So 0 is always in a subring. Okay. So some examples of this are, again, our usual numbers. The integers are a subring of the rational numbers, which are a subring of the real numbers, which are a subring of the complex numbers. Okay. The next thing we're going to discuss some more like properties of rings, sort of like special types of rings. So first note that if you may have that x and y are both non-zero, but xy is equal to 0. In this case, x and y are called zero divisors. Okay. So you have two non-zero ring elements that multiply to 0. So obviously this doesn't happen in our typical numbers, right? You can't multiply two non-zero integers and get 0 out. The common example for where this happens is when you look at modular arithmetic. So numbers mod n form a ring which we typically denote as z by nz. And this notation will kind of make sense after we learn a little bit about ideals. So as a set, you can think of this as 0, 1 through n minus 1. Okay. So in other words, these are the remainders that you can have, mod n. And then addition and multiplication are done normally, but then you have to take the remainder after you do the operation. So as an example, in z mod 4z, you have 0, 1, 2, 3. Then 2 plus 3 is equal to, well, normally, right, we would say 2 plus 3 is 5, and then you take the remainder by 4, and you get 1. So in z mod 4z, 2 plus 3 equals 1. Okay. So as an example of zero divisors, you could just take 2 and 2. So 2 times 2 is, in normal arithmetic, is 4, but then mod 4 is 0. So 2 and 2 are zero divisors, right? And clearly 2 is not 0. So this is a good example of where zero divisors can occur. Okay. If a commutative ring has no zero divisors, then it is called, there's a lot of terminology here. It is called, I usually call it an integral domain. The book that I'm going off of, which is Undergraduate Algebra by Lang, he calls it an integral ring. I think I've seen just the word domain used, so cutting out integral, but I'm a little unsure of that. But I will be calling these integral domains, or I will probably just abbreviate to ID. Okay, so this is a definition. All right, we're almost done. It's a little bit longer than I would have anticipated. So now we're going to look at what happens with multiplicative inverses. So if x in R has a multiplicative inverse, that is some y in R, or xy equals yx equals 1, then x is called a unit, and R star denotes the set of units in R. So the multiplicative, the elements that have multiplicative inverses in R. Note that R star is necessarily non-empty because 1 is its own inverse. So 1 is always in R star. Now R star and the multiplication operator actually form a group. And the reason being, essentially all you have to check is, well, obviously if x has an inverse, then its inverse also has an inverse, right? Like, if x, you know, if x inverse equals y, then y inverse equals x, right? So R star is closed. It has inverses. It has the identity, as we just said. So we have to check it's closed under multiplication. And that is true because the inverse of a product xy can be expressed as y inverse times x inverse. Both of these exist, right? These are elements in R, so we can multiply them. And so the product of two invertible elements is invertible. Or the product of two units is a unit. Okay. And so just one last definition. A commutative ring with R star being the entire set R minus 0. So not basically every non-zero element has an inverse. Then this is called a field. Okay. So as I mentioned before, fields are very important. So they are a type of ring, a very specific type of ring, where all non-zero elements have division, or inverses rather. And so as examples, z, the integers, z is not a field, right? Because think about 2 inverse. There's no integer that multiplies with 2 to give you 1, okay? But Q, the rationals, the reals, and the complex numbers are fields. Okay. So that's all for this video, and in the next one, we will be talking about ideals. So I hope to see you then.